Hey guys, welcome back to CMTEQ channel. This is tutorial 5 on our series of tutorial on IDMT relays calculations. An IDMT relays is a very important element of power system protection. So if you are watching this tutorial for the first time, you may already have some understanding of how an IDMT relays operate. And I will suggest that you pay attention to the details of this tutorial as we break down to solve the problem we have in front of us. You may also opt to watch my previous tutorial on this series. This is tutorial 5, so there is tutorial 1, 2, 3, and 4 that I went through some of the details. And also I've got a tutorial where I explain basically the characteristics curve and how an IDMT relays operate. Now moving on, if you like this tutorial, please don't forget to subscribe to CMTEQ channel. Give the tutorial a thumbs up and you are welcome to drop a comment below and I will reply to it as soon as possible. And this is basically the only way right now that you can support CMTEQ channel, by liking and subscribing and sharing as well. Now in this tutorial we are asked to determine the plug settings and the TMS for the relays A and B, which are relay R1, which is on bus bar A, and relay R2, which is serving as a protection of bus bar B. Okay, using the normal inverse IDMT relays. We spoke about the different characteristics of an IDMT relays, which are the extremely inverse, the very inverse, and the normal inverse. So we are asked to use a normal inverse to solve this problem. Okay, now we've got all the informations here, but there is one crucial information that they've given us here that we need to know. And as we can see on bus bar A, we've got a load of 220 amps and a 125 amps fuse. Bus bar B with a fuse of 100 amp and a load of 200 amps. So those are the loads that these bus bar are drawing. And we have to understand that when this load current are being drawn, the relays is not supposed to trip. The relays must understand that this is normal operation. But there's something different here on bus bar C, which includes an 80 amp fuse and a 180 amp of current, which include an induction motor. Okay, so 180 amps is a load current, but within that 180 amps there is an induction motor that make up that 180 amps. And if we come and we read somewhere here, they say at substation C is a 15 kilowatt motor with a full load current of 28 amp and a run up time of 5 seconds. Okay, so moving on, we then need to calculate our plug settings for the normal load condition and also for the overload conditions, because we have a motor that is attached on bus bar C. Now our calculation will start on the downstream relays. Now that basically means the relay near the end. So if our power system is flowing from here, this is where our ESCOM is connected, so the power is flowing like this down to each load, this load and then this load. So this relay here is the downstream relay and this one is the upstream relay. So for the first calculations, we have to calculate for relay 2, looking out for the load on bus bar C. So what do we have on bus bar C? Well, calculating plug setting for relay B for the load at C. Now we know that the load at C include an induction motor. So what does it mean? That means every time that motor is starting, there is what we call an overload, because there is a high starting current of an induction motor. And what it means is when there is that high starting current, relay 2 here is going to see it as a short circuit, but it doesn't last for a very long time. So the relay must be able to handle that. The relay must be able to notice, okay, that short circuit is a high starting current of the motor, so I should not trip, or what should be the response. But the relay must also operate on a normal load condition. Remember, our fault current for each bus bar have been specified. So bus bar C got a fault current of 6 kiloamp, B 7 kiloamp, and A 8 kiloamp. So we then need to calculate our load current for both the normal load and the overload. So starting for the overload, we've got this expression here. The expression here means, the expression here say we've got 180 amps. That is the total load current. Then we say minus 28 amp plus 6 times 28. What does all of this mean? Don't worry, just hold on. We're going to clarify what all this expression mean. So before I explain this expression here, that is based on the load that is attached on bus bar 2, I would like first to say an induction motor have a starting current that is considered to be a short-term overload. Now this starting current should be able to allow the relay to operate. And this means that starting current should be able to, that means that's high starting current, okay, should be able to allow the relay to operate. Assuming that the time, the tripping time of the relay is longer than the duration of the start of the motor. So how long does the motor take to start? They say here the relay have a run-up time of 5 seconds, okay? So which means your tripping time should be longer than that. Otherwise, if the short time overload lasts longer than the tripping time, the relay will trip because it's going to see it as a short circuit. This is why, because the motor have a full load current of 28 amp. But now we are not calculating for the normal load, because for the normal load, the 28 amps of the motor is already included in the 128. So we're not calculating for the normal load, we're calculating for overload. So this is why we subtract the 28 amp of overload, because the current that we are interested right now is the overload current, which is at startup, okay, at startup, pay attention, the motor current is 6 times higher than the full load current. So if the full load current, that means when the motor have reached its maximum speed, is running optimum, okay, then the load current is 28 amps. So at startup, the high starting current is 6 times that. That's why we have this expression of 6 times 28, which is being added to the current that is already attached on that load. So by removing the minus 28, we now have a load current of other elements, which could be some generator or whatever machines are, okay, or housings and stuff like that. But then we add the 6 times 28 of the overload, the high starting current of the motor. I hope you understand me. If it's unclear to you guys, please just drop a comment. Drop a comment and I will clarify this expression. So the algebra of that expression gives us an overload current of 320 amps. So that means there is a 320 amps of current here when the motor is starting. But that only lasts for 5 seconds. And after that, the current then returns to a normal load of 128, which is 128 amps of current. Having said that, we can then move into calculating the plug settings for this relay based on the load on C. And we're going to apply the formula for the plug settings. Now, if you watch the previous tutorial, we've calculated the TMS and we talked about the plug setting. Now in this tutorial, we're calculating the plug settings now based on the load current on each bus bar, because remember the relay need to be able to operate without breaking when the load is normal. This is why the formula for the plug settings does not use the short circuit current, but it rather use the normal load current to calculate that formula, to calculate the plug setting, and also the full load, the overload current. So we have the first formula here is plug setting for normal load, okay? That is I normal load divided by 0.9 times the CT ratio times the nominal current. Now the nominal current of the relay is either 1 amp or 5 amps. Now we can see that the CT ratios here are 500/1, so automatically our nominal current is 1 amp, which is the secondary current of the CT current transformer. Please guys pay attention. But where is the 0.9 coming from? Well, the 0.9 means the normal full load current must not exceed 90% of the relay settings. So this is why we have to multiply times 0.9, because that is 90%. Because if it exceeds the 90% of the relay setting, then the relay must trip. So that is for the normal load. I hope everything is clear. Now we can apply the formula and calculate the plug setting based on the I normal load. That means it's 180 for normal load current divided by 0.9 with our CT ratio 250/1 and the nominal current of 1 amp. And that is for relay 2, okay? On bus bar B, 250/1, that's the CT ratio. And we find that that is equal to 0.8. which is what? 80% of the tapping, the plug settings, which is 80%. Okay, so you have to always move to the higher next one. So that is 80%. Do we have 80% tapping? I don't know. We're going to see. We then move to calculate the plug setting for overload. And the formula for plug setting for overload is the same overload current. Okay, so this is not normal load, this is overload current. Okay, divided by 1.1. Why now 1.1, not 0.9? Well, because overload current that persists for a while must not be greater than 110% of the relay settings current. Because it's in an overload current that only lasts a short time, but that short time period still should not be higher than 110% of the relay setting current. This is why we divide the equation by 1.1, okay, which is 110%. Just like we did there for normal load. And based on this, we can also calculate, replacing our load overload current of 320 there, the same CT ratio with a 1.1, and we find a value of 1,16. That means it's 116% plug settings. Now 116% plug setting, what does it mean? Now if you watch a tutorial where we talk about the plug setting, you know that there is no 116% plug settings, and there is no 80% plug settings. It goes in steps of 25, 50, 25, okay? So which means from the 80% here, the next one is you should actually go to 100%. But because we have a higher one here based on our overload calculations, so we should go to the next one. And the next one is we select a plug setting of 125%. So which means from our IDMT relay setting here, we need to move this stepping from where it is to 125%, somewhere there. Okay? So now moving on, we're now going to calculate for relay 1 or relay A. Okay? So that is this relay here that is looking out for bus bar A. So that is relay 1 or relay A. And the same apply here. It's either relay 2 or relay B. Okay? This relay A or 1 need to look out for the load current on bus bar B and C. So this current of 200 amps, okay, and this current that we've said the overload here is 320 amps, okay, that current is passing through here and it's splitting to both bus bars. So which means this relay is seeing that combination of both current. So that means when calculating for relay A or 1, you have to add up the two current. So what it means now for overload, because we don't have any other thing here. We just know it's going to be 200 amps because there is no information about something that can induce an overload there. Okay, so it's a 200 amps plus a 320. The 320 is coming from the overload here of the motor that we already calculated at this point. So that gives us a current overload of 520 amps for this relay 1. And for normal load, okay, for normal load, relay 1 is only going to see 200 amps and 180 amps. And that add up to 380. So you have to understand that relay A sees both B and C loads. It sees them both. If you miss that, then there is a problem. Okay? Now, based on these two currents here, we can then calculate the plug settings for this relay. Now notice that this relay here does not see the load that is attached on bus bar A here, because it's placed after the bus bar. That is a critical point to note. Okay, so we're moving on. So applying the formula for normal load for relay A, it's 380, okay, divided by 0.9 with a CT ratio of 500 over 1, and we got 0.84, and that is 84%. What it means is we're going to move to 100% plug settings because there is no 84% plug setting. Now moving on to the overload conditions, the same formula applies with our overload current of 520 that we've calculated there, with the 1.1% that we've already talked about, with the 110%, which is 1.1 that we've already talked about, and our CT ratio, and we find a plug setting for overload of 95%. So which means we have to move to the next one and select 100% plug setting. We can't take, and even that one will take us to 100%. So what it means is the plug settings now for this relay is 100%, and the plug setting for this relay is 125%. Now we are ready to calculate for TMS. Now in order to calculate the TMS for both relay A and B, we need to calculate the multiple of settings, M. And the multiple of settings is then going to assist us to calculate TC, the tripping time, okay? And using the normal inverse formula, and we're going to get to our TMS. Now without wasting any further time, let's dive into it. Now this relay B, looking out for the fault on bus bar C, which is elevated at 6000 amp, will then use the formula of the multiple of settings. So the formula is simple. That is M is equal to I fault divided by the CT ratio times the nominal current times the plug setting. Now you can see that this is almost the same formula as the formula of the plug setting here. The only difference now here, we are now using the fault current instead of the load current. And we now also have the plug settings in the formula because we just calculated it using the previous formula. Now from here, you guessed it, you're just going to replace the values, and you got a fault current of 6000 amp at that bus bar, okay? And this relay, we know it's a 250 over 1, and we've got a nominal current of 1, and here is our plug settings of 1.25, which is 125%, and we find an M of 19.2. What do we do then with this M? This M will then be used in the normal inverse formula of TC, and that formula is TC is equal to 3 over log M. Having replaced M with a 19.2 that we just calculated there, we get a value of TC that is equal to 2.34 seconds. Now what we're going to do with this TC? Well, this TC is going to be used to calculate TMS. We know what's the formula for TMS. Formula for TMS is TA, the actual time, over TC. Okay? But then we know that the time required to discriminate with a fuse is 0.3 seconds. So that means TA is equal to 0.3 seconds. Now, why do we say that? Because we've got fuses that are placed on each load bar to protect. Okay? So we have to take account of that. that is 0.3 seconds. Now if there were no fuse, then we would use the normal discrimination time of 0.4 seconds. So this is now our TA, and from there we can then calculate the TMS, TA over TC, that is 0.3 over 2,34 seconds, and we got the TMS of 0,13 seconds. Okay, I know this tutorial have been long. I hope you've been patient enough to watch and understand these fundamentals. So I'm going to stop it here. Next tutorial will be part 2, where I'm going to complete the TMS for relay A, and then we're going to also calculate the actual tripping time for this relay based on the fault on bus bar A, because this relay A need to also trip in case there is a short circuit on bus bar A, which is 8000. So we're going to see that in the next upcoming tutorial. Please stay tuned on CMTEQ channel, and don't forget to subscribe and give the tutorial a thumbs up. Cheers.